This video is an example of designing logic circuits. We'll use this as an example. Determine the truth table for a safe with an electronic alarm that will sound an alarm if the safe is opened after the alarm is set, or if the power is cut and the door is open, but not if the alarm is turned off before opening the door. So here we have a truth table. We'll list our inputs on the left. That'll be the state of the power, if it's on or off, if the alarm is set or not, and if the door is open or closed. Then our output will be on the right. That will be the alarm. So depending on the state of our inputs, we want our alarm to sound. So let's start filling out our truth table. If the power is not turned on, but the alarm is not set, and the door is not open, we don't want an alarm to sound. Let's change these conditions one at a time. Leave the power not on, the alarm not set, but the door open. But if the power is not on and the alarm has not been set, we still don't want the alarm to sound. Then let's change the next setting. We'll leave the power off, set the alarm, and the door is open. Now this is a condition where the alarm has been set, but the power has been cut. In this case, we want the alarm to sound. If the power is off, the alarm has been set, but the door is closed, we don't want the alarm to sound. Now if the power is turned on, but the alarm has not been set, and the door is closed, we don't want the alarm to sound. If the power is on, the alarm has not been set, but the door is open, that's an example of the owner opening the safe after he's turned the alarm set off. So we don't want the alarm to sound in that case. If the power is on, the alarm has been set, and the door is open, then we want the alarm to sound. That would be the case of someone breaking into the safe. In our last condition, where the power is on, the alarm is set, and the door is closed, that's the condition where our safe is doing its job. If things are in the safe, we don't want the alarm going off. So here are all the conditions on our truth table. Now after determining a truth table, we need to determine what kind of logic gates and how many of each kind we're going to need to use to build our circuit. But before we do that, we should optimize our logic circuit by eliminating any unnecessary or redundant gates and redrawing our truth table. So the way I see it, there are only two conditions under which we want our alarm to go off. This condition and this condition. In both cases, you can look at this and see that the state of the power is irrelevant. That we want the alarm to go off if the alarm is set and the door is open. The condition of the power doesn't matter either way. So that's an unnecessary condition. So let's eliminate that. This new truth table describes our inputs, two inputs only, the condition of the setting of the alarm and the condition of the door, and the output is the alarm. And it shows that under only one condition, if the alarm is set and the door is open, will the alarm sound. The other conditions leave the alarm off. This is the truth table we need to design our logic circuit. And looking at this, we have only under the condition of the set and the door do we have an alarm sound. So this is a AND logic function, or we'll need an AND gate. This is the logic symbol for an AND gate that has two inputs. In this case, the condition of the set and the condition of the door, and one output, the alarm. And only under the condition that both the alarm is set and the door is open will the alarm sound. And hopefully this gives you an example of a simple example of how to design a logic circuit, or what logic you're going to need to design an electronic circuit, and how to use a truth table and how to optimize that truth table in some way to try to come up with a good, efficient design.